Okay, we can start. So good morning, everyone. I'm Joseph Farah, Microfluidic Application Specialist at Fluigent, and I'm pleased today to welcome you to this webinar on complex emulsions, where we will explore how to optimize the production, improve control, and achieve monodispersity using modern flow technologies. Joining me today are two expert speakers, Dr. Adrien Dewandre, he's a technology lead at Secoya Technologies, and Professor Shijin Lin from the Department of Chemistry at the National Donghua University from Taiwan. Dr. Dewandre brings in-depth experience in high-precision microfabrications and microfluidics, and Professor Lin leads an innovative research group focusing on responsive luminescent materials and microfluidic sensing platforms. So the agenda for today, we will begin by reviewing what emulsions are, how they are used, and why they matter. We will look at the limitation of classical methods, the emergence of microfluidics, and how advanced flow control systems are enabling new possibilities in this field. You are encouraged to submit your questions through the Q&R or Q&A panel at the bottom of the Zoom screen. And we will address them after, during the end of the webinar. So let's begin. Before diving into definitions, let's start with something familiar. Emulsions are all around us, and we encounter them daily, often without realizing it. Think, for example, of milk, which is a classical oil and water emulsion, mayonnaise, which is stabilized with egg yolk, for example, the salad dressings, often are temporary emulsions that require shaking, and sunscreen, which combines oil and water phases for skin delivery. Each of these emulsions, which are like two immiscible liquids, typically oil and water, blended into a stable mixture. Though they may look simple, these systems are chemically and physically complex. They require surfactants to remain stable, and any small variation in how they are produced can dramatically affect their properties. So at its core, an emulsion is a system where one liquid is dispersed into another in the form of the droplet. The most basic type is the single emulsion, where either oil is dispersed in water or vice versa. They are stabilized by surfactants, which are like molecules that can reduce the interfacial tension and prevent the droplets from coalescence. Moving beyond the single emulsion, we have double emulsions, such as water and oil in water, or vice versa again, oil and water in oil, which involve three phases and enable compartmentalization. These are specifically used, for example, for applications like controlleries or encapsulations of actives. More advanced systems fall into the category of complex emulsion. This can include multiple internal phases or polymeric architecture, like core shell, capsules, or structured beads. Complex emulsions enable multifunctional delivery and dynamic control over the reliefs or reactivity. But producing them requires high level of control, something that classical methods often struggle to provide. So in the next couple of slides, we'll check the difference between the classical methods and the microfluidic methods that is emerging. Historically, emulsions have been produced using mechanical techniques like high schist mixing, as you can see in the images, or ultrasonications or homogenization. These methods are quick, scalable. They are used across industries, from food, cosmetics to pharmaceuticals. However, their limitations become clear when we require precision. These methods tend to produce polydispersed droplets, meaning a broad distributions of size, as we can see on the image on the right. These mechanical stress involved can also degrade sensitive components when we are considering encapsulations of APIs or cells and so on. And it's challenging to produce the same structure or distribution between batches. Most importantly, classical techniques fall short when it comes to making complex multi-phases emulsions with well-controlled architectures. And that's where microfluidics offers a powerful alternative. So microfluidics, which emerged now as a transformative approach for emulsion production, by precisely manipulating fluids in microscale channels, it is possible to generate monodispersed droplets. Droplets with like uniform shape and sizes, with an advanced control over their sizes and formulations. The confinement of flows within well-defined geometries allowed for sequential emulsification, layer-by-layer phase addition, and accurate control of internal structures. However, this level of control doesn't come free, as you may know. The microfluidic setup itself can be complex and tricky to elaborate, as it involves not just the microfluidic chip in order to create the generation of droplets, but also the entire flow control systems from reservoirs, valves, sensors, and the software to control all this setup. To help us understand how this can be addressed from a technological perspective, I'm pleased to hand it over now to Dr. Adrien Dewandre in order to explain more the advantages of one of the chips that are available, the RayDrop, and the technology behind it. Adrien has been at the, let's say, forefront of developing microfluidics platforms now. He started in physics at the University of Namur and afterwards worked as a teaching assistant in Brussels, and then managed several high precision projects in micromachining and for medical and microfluidics applications. He's now leading innovation in microfluidic technologies at Secoya. Adrien, the floor is yours.
Thank you, Joseph. Okay. Thank you, Joseph. I'm very pleased to participate to this webinar organized by our partner Fluigent, longtime partner, and to introduce you to our emulsification technology, that we developed at Secoya. So I will start very shortly by an introduction to our company. The story of Secoya technology started 10 years ago, more than 10 years ago, when 5 scientists developed in a lab of the Université Libre de Bruxelles, ULB, expertise in flow chemistry, microfluidics, millifluidics, and chemical intensification. And 7 years later, we founded a spin-off company to valorize the patents filed during this incubation step. And now today, Secoya is a company of about 12 people, and we develop and offer services and equipment in the development and manufacturing of biopharma products, actually. We are based in Louvain-la-Neuve, so close to Brussels in Belgium. And maybe you may ask why the name Secoya? And that is because at the time we had this idea of a big thing made possible by the continuous transport of fluid in small capillaries, as it works in tree, even in the biggest one. And actually, the Secoya tree is probably one of the biggest microreactors in the world. So by encapsulation, we refer to the controlled integration of molecules in a protective environment, usually as spherical beads or a microcapsule with a solid shell and a liquid core. And the typical size of these objects is about 100 microns. So we are not in the world of nanoparticles. The typical size is about 100 microns. And the materials used to make them are generally the polymers used in pharma applications like PLGA, chitosan, alginate, etc., depending on the goal on the application. So the objective of this encapsulation depends on your application, of course. It can be sustained or targeted drug release, protection of the encapsulated molecule from the environment, etc. We can also encapsulate cells for subsequent sorting using flow cytometry, FACS instruments, or for cell culture in a controlled environment. As Joseph just said, to encapsulate a molecule in a particle, you first need to produce an emulsion of one liquid in another non-miscible liquid phase. In a standard batch process, the fast stirring is commonly used. And then after a drying process, depending on the formulation, a solid particle is obtained. These particles typically present a large size distribution and a poor sphericity, what is not ideal for precise loading. On the contrary, using microfluidics tools allows to directly produce droplets, then particles with a very narrow size distribution, and you can fine-tune the size of your droplets while always maintaining a good sphericity. The benefits of using microfluidics technology are multiple. You have a high encapsulation efficiency, a precise loading of the cargo inside the droplets or the microcapsules. What you get is a uniformity of the release kinetics, and you can work with a small volume of material for development steps. That is very interesting because you can use a very expensive and very low volume materials to make a lot of experiments in a fast screening step on formulation. Okay, now let's have a look at what tools are available to produce droplets in microfluidics. You maybe recognize some of these devices. The planar chips with channels engraved in glass, PDMS, or plastic are commonly commercially available. I used them intensively when I was at the university, and I was very quickly confronted to their limitation. Because of this planar geometry, the droplet phase is in contact with the top and the bottom of the channel at the flow focusing junction. And that is why, to prevent the wetting issues, the wall of this channel must be coated with an hydrophobic or hydrophilic coating, depending on your formulation. And with the formulation I tested at the time, the hydrophobic coating resisted approximately 20 minutes, and then I could throw the chip away. There is another option. In academic lab, droplet generators based on the alignment of a glass capillary were developed by the Wade's team in Harvard at the time. They don't need coating to be applied because of the cylindrical geometry of the system. The droplet is totally surrounded by the continuous phase, so there is no contact between the droplets and the wall of this device. So they're also permitted to produce double emulsion, a drop in a drop, but this kind of device never reached the markets because it is very difficult to fabricate and difficult to reproduce. So what was missing at the time was a device allowing to produce single and double emulsion with a reproducible fabrication process with standard connection like HPLC type and a device that was robust and versatile, so no coating. So there was a room for a novel device. We call it the RayDrop. And I'm now going to show you how it works using this movie. I hope you can see it. Okay, so the RayDrop is the droplet generator developed at Secoya. It is based, the goal of this device is to produce single and double emulsion. And it is based on the alignment of two inserts in a metallic chamber, one insert on the left on your screen supporting a glass capillary. And at the end of this glass capillary, there is an injection nozzle, 3D printed injection nozzle. In front of this glass capillary, there is another glass capillary for the extraction of the droplets. First, we introduce the continuous phase to fill the chamber and the pressure with the continuous phase. Then we connect the droplet phase. And we finally collect a tubing to extract the emulsion from the device. At the junction of the nozzle and the extraction capillary, the fluid coming out from the nozzle is stretched by the continuous phase, leading to the formation of very monodispersed droplets. And as you can see, there is no contact between the droplets and the wall of the extraction capillary. So there is no wetting issue in this system. Now, if you want to produce double emulsion, we just need to replace the injection insert by an insert able to carry two phases, a core phase and a shell phase. And at the junction of this special nozzle and the extraction capillary, the core phase is totally surrounded by the shell phase, surrounded by the continuous phase, leading to the formation in one step of a double emulsion. So in summary, what Secoya developed is a device called a RayDrop, allowing to produce simple and double emulsion. It relies on a cylindrical geometry, so no coating is needed. It is interfaced with pump, other equipment, with using standard connection, HPLC type. And finally, it is composed of 3 parts, easy to disassemble for cleaning. So now you may ask what kind of size can be reached using this system. With a fixed geometry, I mean the geometry of the nozzle and the extraction capillary, you can reach one range of size, and you can fine tune the size in this range by adapting the flow rates. And if you want to change the geometry, to change this range of size, you just need to change the geometry. So you can, we propose different couples of injection nozzle and glass capillary to be able to produce single and double emulsion between 25 and 400 microns. So you just need to change the injection insert and the collection insert to go from this range to the other range. Okay, so we have this tool. Let's have a look on what can be done with this equipment. And to demonstrate the capabilities of this instrument, at Secoya and with Fluigent, we developed case studies based on the most common formulation described in literature. So the goal here is not to make rocket science, it's just to show what can be done with this instrument in simple and double emulsion using the most used polymers. Okay, we start with a single emulsion process to produce microbeads of PLGA. PLGA is a polymer FDA approved, and it is widely used in pharma applications. In this case, the precipitation of the polymer initially in solution in an organic solvent is due to the solvent extraction in the water continuous phase in the tubing just after the formation of the droplets. With this process, we tested the encapsulation of lysozyme in suspension, and we reached a very high encapsulation efficiency, more than 95% of the lysozyme was encapsulated in the PLGA particles. So there was a very small fraction of the proteins lost in the process. Then we increased the complexity using a similar process to produce a double emulsion with a liquid core surrounded by a solid PLGA shell. The process is very similar, so the PLGA precipitates after solvent extraction in the water continuous phase. And in this case, we use isopropyl acetate as a solvent for the PLGA. It is less miscible with water than ethyl acetate, and that's why the extraction continues, is slower and continues in the collection bath. We use this process to encapsulate peptides tagged with fluorescein that you can see below on the slides. And the encapsulation efficiency was very good, with no visible material outside of the microcapsules. In the next case, we developed a process based on a double emulsion water in oil in water to produce alginate beads for cell encapsulation. So there exists single emulsion process for alginate beads because that is just that is not a double capsule at the end. It is a bead. So you can do that in single emulsion, but this process relies on a water in oil emulsion. And at some point in this process, you need to remove a huge quantity of oil. And this step is often dirty and complex, but it is necessary if you want to resuspend your alginate beads in a solution adapted to, in a solution adapted to cell culture. So we developed an alternative process based on a double emulsion setup with alginate in the core, a very thin shell of oleic acid that is compatible with cell. We tested that compatibility, and water as the continuous phase. The double emulsion are collected in a bath with calcium chloride, which diffuses through the oil shell, causing the alginate to gel and shrink. And then when the particles are solid, they can be easily separated from the oil by a gentle centrifugation and then collected in suspension in water. So this process with a small amount of biocompatible oil and no washing step with organic solvent is definitely more compatible with cell survival and growth. That's all in water process. We had the opportunity to test this process in the collaboration with the Université de Bordeaux for the encapsulation of kidney cells. You can see on this movie, I don't know if the resolution of what you see is high enough to see that there is, let's say, between 10 and 40 cells in each droplets double emulsion that we produce. And at the end, we obtain a high viability and cell proliferation in the form of cohesive spheroids. A publication is on work on this project. It will be very soon published. And the last case of my presentation is a process that we developed for the study of crystallization condition in microcapsules made of a liquid core surrounded by a UV cross-linkable shell, a resin shell actually. And the goal here was to produce a lot of similar microcapsules encapsulating molecules and then screen the conditions leading to the formation in crystal inside these microcapsules. In this example, lysozyme is encapsulated in the core with sodium chloride, 5% sodium chloride, and the shell made of a resin is solidified by passing below a UV lamp, and the solid capsules are collected in a sodium chloride bath, but with a higher concentration of salt. Water will then diffuses through the shell until spontaneous nucleation condition is reached in the core, and then the crystal growth. And in a fraction of the capsule, what we get is a single monocrystal that can be directly analyzed by X-ray diffraction in the capsule, because the capsule has dimension that fits the sample holder, and the shell is transparent to X-ray. So with these methods, you can very quickly screen a large number of crystallization conditions with a minimum amount of material, and you can then send your crystal for analysis to a colleague in another part of the world using, let's say, a FedEx sending, because the shell is very solid and will protect your crystal from the environment. And we published this study in ChemCom, and then we obtained funding to continue this very, very interesting screening process in microcapsules. Okay, there are a lot of other case studies. You can find this application on our website and the website of Fluigent, but for me, I think that it's enough for the moment. I will let the floor to Professor Lin. Thank you for your attention.
Okay. So I'm trying to stream. So thank you for a very interesting case study and Joseph introduction. So I will going to share my screen. Okay. So I'm going to share with my research about fluorescent complex emulsion. So first, I would in our system, the complex emulsion, we are focusing on the hydrocarbon oil and fluorocarbon oil. It's a little bit different from the oil in water oil or water in oil or water system. We had both. They are both oil, but one is a hydrocarbon, the other is fluorocarbon. That simply make the complex emulsion is basically because hydrocarbon, fluorocarbon is a lower miscible temperature, so heat it up, become monodispersed, and a few drops to the surfactant solution, and then further we can make the complex emulsions, okay, with the hydrocarbon and fluorocarbon. So basically, we are very interested in this system because the complex emulsion is a kind of a dynamic system. So basically, they can change the morphology based on the surfactant concentrations or surfactant effectiveness. So it's very sensitive to environmental conditions. So you can see that the morphology change immediately when they inject the surfactant from the bottom right and flow to the upper left. So you can see the complex emulsion change the morphology. So one of the interesting optical property is that complex emulsion can be a micro lens. So when they become the genus, like this system, the light was totally transparent. But for the double emulsion, there's either light will become focusing or diverging. So this can be used as if they put the light sensitive surfactant in the system. So when they share the line, they can change the morphology from the double emulsion to genus. So it can also they can also change the transparency from the droplets. And this work at very beginning is initiated by Tim Swagger. Well, he's a professor in Massachusetts Institute of Technology. So he established this material, and he also developed a very interesting way for sensing. That is, use the light transparency. For example, this is a readable, this is unreadable, means there's some analyte we can detect. Okay, and then there are new aqueous sensor material, complex emulsion, and there are more and more applications based on the optical properties. For example, they can monitor water hardness, it can detect the peripheral alkyl substance, and also the bio sensors. They can monitor the enzyme activity, even the pathogen like Listeria, E. coli. So all of these systems, they use the complex emulsion, but sometimes they need the well-aligned droplets to have a good signal noise ratio. So I'm thinking in our system, we define a system that is, we don't need the droplets just well sitting there. Okay, just based on the fluorescence turn on, turn off, and we can observe the environmental change. So simply, we design this system, we use a fluorescence switch. Okay, for example, we can have a double emulsion, it shows a fluorescent turn on, and the other double emulsion shows a fluorescence turn off. Okay, and we synthesize the this chromophore. I just skipped this, but this chromophore is very sensitive to water. So if they put in a hydrocarbon water interface, the fluorescence will be quenched. But if the dye is in the inner double emulsions, the fluorescence will turn on. So here we change the morphology. Okay, if we change the morphology from the this is a hydrocarbon inside to the hydrocarbon outside, and this dye has a chance to attach or to contact water. So when they're increasing the SDS proportion and the hydrocarbon will be outside, we can see the red line is the emission become weaker. Okay, and this is also proportion to the hydrocarbon exposure to water surface area. Okay, and the blue dot is the reference. You can see the reference has no change. Emission has no change. Okay, based on the morphology change. So this is a quite interesting system. We can have a emission as a signal readout, not only the morphology. And then we develop a system. We replace the hydrophilic side with a peptide. So this peptide has a hydrophilic end and a hydrophobic end. And the linkage here is a lysine. So lysine is very sensitive to trypsin. And okay, so if we add the trypsin in the system, okay, so this hydrophilic part will be cleaved. So the morphology will change from the hydrocarbon outside to the hydrocarbon inside. So we can see the fluorescence turn on. But without the trypsin, okay, we only see a very weak emission in that case for the hydrocarbon outside. So this is the first case we demonstrate we can use fluorescence as a signal readout for the complex emulsion. And then this is the first system we developed. And then we developed the other system is to use the other dye. Okay, so this is the other dyes. Okay, you can see here. This is a hydrocarbon, fluorocarbon, water, double emulsion. So it means that if we have a fluorocarbon outside, it shows a green emission at the shell. Okay, and in the core, it shows blue emission. But when we change to the hydrocarbon outside, the green emission disappeared, and we only see the blue emission. And this is based on this amphiphilic dyes. So this amphiphilic dye is also very important because usually the complex emulsion, the stable need surfactant. And this is a surfactant. So we don't need to add external surfactant to stabilize the complex emulsion. And then this, okay, you can see this is a very beautiful complex emulsion. And this is based, we make this droplets based on the RayDrop. And at that time, we use the single emulsion RayDrop, okay, because we use the properties that hydrocarbon, fluorocarbon, they can miscible at a higher temperature. So we put this in a heating block, okay, and then inject to the single emulsion RayDrop, and we can get lots of monodispersed complex emulsion in that case. So, and then we develop microfluidic chips. Okay, so we design this multiple flow chips. Okay, and each well, okay, the size is 70 micron, and the height is 1000 micron. So we can we flow all the droplets inside the chips, and each well can stay. Each droplet can stay in the well and very nicely. So I just show the video. Okay, we can inject all the droplets into the micro wells. Okay, because of the droplet size is super monodispersed, so each well can only stay one droplets. Okay, so we can make this as a very good platform to keep our droplet inside. And then we are going to develop this system into a new sensor material. So because we have the dye, one chain is a PEG chain, a polyethylene glycol chain. The hydrophilic chain is a PEG chain. And PEG chain has a very unique, can have an interaction with iodine and make the PEG chain less hydrophilic. So this is a petri dish. Okay, if we inject the iodine inside, at the middle of the petri dish, okay, it will change the morphology from to the hydrocarbon outside. But the outside layer, it becomes genus, and the outer layer, it becomes the fluorocarbon outside. Okay, so based on the iodine concentration, we observe the morphology difference. So this is a platform we can play for the sensing, especially we integrate with the flow chips, and we can make it as a flow inject analysis. So this is the video. Okay, we can show with you is that. So left one, okay, we inject the iodine from the left. Okay, and because all the droplets just stay in the wells. Okay, so we can see the when the iodine flow is continuous flow and the morphology change from the double emulsion to genus, okay, to the inverted double emulsion. Okay, so based on this, okay, we can develop a method, okay, for the sensing. So simply say is we have this microfluidic chips, and we focus on the middle of the complex of the middle of the flow chips. Okay, and because we know how many droplets in the flow in this flow chips. Okay, so when we inject the iodine, okay, and then this flow, okay, we observe the certain in the middle of these chips. Okay, and we monitor the morphology change from the hydrocarbon to fluorocarbon in water to genus. We change we monitor the time, and first the iodine concentration. We find this good correlation. Okay, so basically we develop a method is simply we can monitor the morphology, and then we can estimate the concentration in the analyte concentration in the aqueous solution, especially this is a flow system. Okay, instead of a previous result, they probably use a petri dish, and they use this that must be well stayed. Okay, but you can see here the flow, based on the flow, okay, the droplet is moving, so it's hard to use the optical effect to see the change. Okay, but here we can directly see the morphology. Okay, and then do the flow inject analysis. So this is a result we already published 2 years ago. And after that, okay, we already buy a new RayDrop chips for the complex emulsion. Okay, so the more fluorescent complex emulsions on the works on the way. Okay, so the short summary for the fluorescence complex emulsions, we use this hydrocarbon fluorocarbon platform, and as a complex emulsion, I think this is a promising sensing platform for the flow inject and analysis. Okay, so this is a part of probably is of my jobs during the complex emulsion, our published result. Okay, so actually, well, I just want to borrow you guys a short time, okay, because I think most of them didn't know Donghua University. We are in the eastern Taiwan, and you may know Taipei, maybe know Kaohsiung, but we are in the eastern Taiwan. We are very close to the Pacific Ocean. Okay, we have a very good indigenous culture, and this is our campus. And we have a good lake and very beautiful sightseeing. Okay, So welcome to FlowEZ Hualien. And this is my team. So I think most of them have done by Narari Rakesh, and he's my PhD students, and others done by this Justin, and they are very good complex emulsion, I would say, the players. Okay, and mostly I thank Fluigent and also Secoya's support to my research. Okay, I'm happy to take any questions.
Thank you, Professor Lin, and also Dr. Adrien for these presentations, these two talks. I'm sure I will have some questions after this short, after these two talks. So I would like to summarize. To summarize these two talks. So basically, we saw some applications in real life for the complex emulsions, and from single to double to complex. We discovered with Dr. Dewandre what are the advantages of the RayDrop compared to the market, with some various applications from the encapsulations, droplet or beads generations, double emulsions, and the encapsulation of materials. And afterwards, so it can be a wide variety, as explained by Professor Lin. Like we will have a variety of applications, especially, for example, in the complex emulsions that he produced with the fluorescence emissions. So for this, just before moving, a quick word about Fluigent for the participants who are not familiar with it. So we have the expertise in controlling the flow at a micrometric scale. Our pressure controllers are used in several big research around the world, and we are based in Paris, but we are also present with the subsidiary in the US and a wide network of distributors across Asia. For just to have a quick comparisons about why choose the pressure controllers to the syringe pumps. The pressure controllers like that will have are based on pressure, so you don't have any mechanical force in order to avoid the pulse when you are doing when you are controlling the flow. This is characterized by the fast flow rate, by a fast response time, and settling and set time. And in this case, like you will have more monodispersity, and you control faster the emulsions compared to the syringe pumps, and avoid the disruption when you are creating your own droplets. So as Dr. Dewandre mentioned, there's been like a long collaboration between Fluigent and Secoya. We combined our expertise in the expertise of Secoya in droplet generations and our expertise in fluent management in order to create packs, platforms that combines the two expertise, and in this case facilitate as much as possible the creations of droplets for a wide variety of applications, simple and double emulsion. So don't hesitate to contact us if you have any inquiries, questions, or even talks to adapt and function of the applications that you are searching for and the possibilities of collaborations. I would like to thank Dr. Dewandre again and Professor Lin for this talk and this webinar. Thank you for your presence, and thank you for your time, and see you in the upcoming webinar from Fluigent. Have a nice day.
Thank you. Have a nice day. Bye-bye.
Bye-bye.